Welcome back for the first video from section 2.1, talking about matrix operations. So let A be a m by n matrix. We use the following convention for naming the entries of the matrix. We want to write aij, lowercase aij, for the number in the ith row and jth column. So in row 1, column 1, it's a1, 1. If we're still in row 1 in column 2, this is a1, 2. And so on. This is A1J all the way down to A1. And what are we doing? If it's M by N, then this is the nth column. A1N is there. And then similarly, this will be A2, 1 down to AI1 and AM1. And so if we're in row I and column J, so right here, let's maybe, yeah, then we're this entry aij. Okay, so as always, it's down and then over. So down I over j is aij. Okay, and we call, look, we've got A22 is right here. There's this nice like diagonal that we call the main diagonal. A matrix itself is called, yeah, these are the diagonal entries, the ones where you go over and down the same amount. We call a matrix diagonal if those are the only non-zero terms, so that if everything outside of this diagonal is 0, then you've got a diagonal matrix. So in particular, yeah, the identity matrix, the 3x3 identity matrix is a diagonal matrix. The n by n identity matrix is also a diagonal matrix. We had dilation matrix last video that was all 2s in the diagonal. Again, diagonal matrix. Okay. So let's see. Yeah, we can add matrices if they're the same size. And then you do the obvious thing, right? Someone puts a gun to your head, says add these matrices. You do the obvious thing and hope that it's right. You add 1 and -1, you get 0. You add 2 and 0, you get 2. You add 3 and -1, you get 2. And the other row, 0 plus 0 is 0. 5 plus 1 is 6. 10 plus 2 is 12. And you'd be right. You follow your nose, sometimes it works out. And similarly for scalar multiplication, if we want to double a matrix, we should just add it to itself twice. And so we should double all the entries. So this becomes 2, 4, 6, 0, 10, 20. Okay, and this next theorem says lots of the sort of obvious properties of multiplication and addition still hold. So in particular, yeah, if A, B, and C are matrices of the same size, and R and S are any scalars, then it doesn't matter the order that we add them in. It doesn't matter how we bracket the addition. We have this 0 matrix with the property that if we add it to any matrix A, we get back A again. If you multiply a sum of matrices by a scalar, that's the same as performing the scalar multiplication first and then the matrix addition. Again, if you multiply a matrix A by a scalar, that's the sum of 2 scalars. You could just hit A with each of these scalars and then take the sum. And then it doesn't matter if we do matrix multiplication first and then twice, or if we do scalar multiplication and then matrix multiplication, or scalar matrix multiplication. Okay, so that's addition and scalar multiplication of matrices. We don't use tons of that, but those properties are there. The more interesting thing is trying to work towards multiplying 2 matrices. So we know that if A is an m by n matrix and X is a vector in Rn, then AX is now a vector in Rm. And additionally, if B is some p by m matrix, then what? Then we have AX is a vector in Rm, B is p by m, so then BAX is now a vector in Rp. So let's see how this is going to help us figure out what B times A ought to be. So if A is the matrix whose columns are vectors A1, A2 up through AN, and B is the matrix whose columns are B1, B2 up through BM, and we hit, if we hit A with a vector X, then we just get back the linear combination of the columns of A weighted by the vector X. And we can, here we go. We can do the same thing with BAX. This will just be be applied to whatever we had upstairs. So this is a1 x1 plus a2 x2 all the way up to am x m. M or n, David? M or n? N, sorry. A-N. Okay. And we know that matrix multiplication splits up over addition really nicely, so this will just become, yeah. We'll do all the steps. So this is b applied to the vector a1 x1 plus b applied to the vector a2 x2 b applied to the vector an xn. And one of the many properties we know about applying or multiplying a matrix and a vector is that we can actually pull out scalars. So this becomes x1 b times a1 plus x2 b. It makes more sense. Try this again. It makes more sense to pull out the scalar in the other direction. ba1 times x1 plus ba2 x2 ban xn. And the reason I wanted to keep the x's on this side is because it looks like we've got matrix multiplication again, where these are the columns of some matrix, and x are the weights again. So it looks like we've got a matrix that's ba1. These columns are ba1, ba2, all the way up to ban, and we're just applying this to the vector x. So we should really call this the matrix BA. This is the matrix BA. Oh. Okay, so there's the where does this definition come from? How do you actually compute it? We'll go through a couple of examples and that'll make it much more clear. So let's take A to be this matrix and B to be that one. What we want to do, our claim is just that we should apply B, we should apply B to each of these columns, and that'll give you the columns for BA. So let's label these really quick. This is A1, A2, A3, A4. Yeah. So yeah, BA is just B applied to A1, B applied to A2, B applied to A3, B applied to A4. And so we need to figure out what BA1 is. 2, -1, 3, 1, 4, -2. And then A1 was just 1, 2, 3. And by now we know how to apply or multiply a matrix with vector. So we're just going to get what? I always enjoy draw these arrows, and otherwise I forget. So it's going to be 2 times 1 plus -1 times 2 plus 3 times 3. And then we go downstairs. Be 1 times 1 plus 4 times 2 plus -2 times 3. Should get back what? 9. And can't be right. Yeah. 9 and 3. All right. Okay. So let's compute BA2. 2, -1, 3, 1, 4, -2. And now we're hitting out with the vector 0, 1, 4. So we're getting, I'll save you the hassle of watching me do this over and over and over again. This is going to be 11, -4, BA3, 2, 1, -1, 4, 3, -2, 5, -1, 2. So again, we're picking up 2 times 5 minus 1 times -1 plus 2 times 2. It's going to give us 17. Oops. 17, 3. BA4. Okay, we'll do one more. We'll do one more by brute force, or showing all the details by popular demand that I'm making up in my head. The third column is -3, 2, -1. Okay, so then just to make sure we're all on the same page, 2 times -3, 2 times -3, plus -1 times 2, plus 3 times -2, and then 1 times -3, plus 4 times 2, plus -2 times -1. And lo and behold, we get what? -11, 7. Okay, so that means that BA is just the matrix that had all of these results as its columns. So it should be 9, 3, 11, -4, 17, -3, -11, 7. Okay, and one thing you'll notice is that we really needed this to be a 3x1 vector. If it was 4x1 or 2x1, we've been at luck because not all matrices can be fed all vectors. So maybe we notice A is 3x4, B is 2x3. Oops. And then BA is what? It's 2x4. And this works in general. We've got BA was 2x3, and this is 3x4. You've got to like glue them together at the common dimension, and the result is the other two. So we like squash these two together and get 2x4 for the product. That's one way to think about it. Let's do another example. We'll do a fun example. I like this example where we've got a matrix that is 1x3, let's say, and B is 3x1. So here's with an AB. It's actually just going to be a number, right? 1, 2, 3, -1, 0, 2. Right, there's only one row and one column. So we get back a -1, or 1 times -1 plus 2 times 0 plus 3 times 2, which is 5. And this is called the dot product, which will, if you've taken vector calculus, you've seen this already. If you haven't, well, you're going to become friends with this product. Dot product. I think we'll use it later on too, actually. Dot product of vectors. Here we need to sort of make believe that A is a proper vector instead of a sideways vector. We could also multiply. So note, BA also makes sense here. And then with me waving my hands and beating my gong, or like trying to get your attention, they're not at all. They're not even close to the same thing. A times B is a scalar value. It's 5. B times A is going to be a 3x3 matrix. So of all the like funny properties we can expect for matrix multiplication, we can immediately forget about. We can immediately forget about the possibility that A times B is equal to B times A. Right out. Absolutely not. Hard pass. No. Nope. I don't know how to say. I'm running out of ways of negating this. But it can't be done. It's not happening. So let's see what happens. No, I didn't. Yeah, here we go. So if we did this, then what we want is to apply this matrix to each of these columns. And the result, I'll let you, is going to be what? -1, 0, 2 is we're applying each of these to the scalar 1, and then -2, 0, 4. It's sort of a boring matrix, -3, 0, 6. But that's what happens. That's B times A. Okay, where are we here? Oh yeah, right. So then the last thing I was going to note is that we don't need to suffer through this BA1, BA2, BA3, BA4 thing every time. Once you get the hang of this a little bit, oh, there we go. We can find this product just by taking the dot product of the ith row of A and the jth column of B. So let's do that matrix multiplication again a little quicker this time. So the first row of A and the first row of B should give us our 1, 1 number. So it should be, I'm going to make little arrows here, otherwise I'll lose it. Boom, boom. So 1 times 1 plus 0 times 0, that's just 1. And then we can move our arrows down. Oh. Now we've got -1 times 1 plus 2 times 0 is -1. And move this down one more time. 0 times 1, 3 times 0 is just 0. Oh. And then we move this arrow over, move this one back up. Okay, now we've got 1 times 0 plus 0 times 1, that's another 0. Move this down. This is literally what I think of every time I need to multiply two matrices. -1 times 0, 2 times 1 is 2. The little arrows moving around. 0 times 0, 3 times 1 is 3. Okay, and move this over. Oh. Okay, 1 times 0, 0, 0 times 1 is 0. Boom. Okay, -1 times 0, 0, 2 times 1 is 2. 0 times 0, 0, 3 times 1 is 3. Okay, and finally, let's just do this one really quick. 1 and 2. So it's going to be 1. We've got -1 plus 4 is 3, and we've got 6. Okay. Did it. We can get rid of our little arrows to remind ourselves. Okay. I'll see you in a sec for the next video from section 2.1. Take care, everybody.